Hi everyone, I'm Romil. I'm a co-creator of the SkyPilot project, and I'm super excited to be here to be talking about how do you build multi-cloud AI platforms, but without the pain of everything that comes with multi-cloud. So building AI platforms is not easy, right? And let me show you why. So let's look at OpenAI's cloud infra journey. So back in 2016, OpenAI and Microsoft signed a deal to have Azure as like the exclusive cloud provider for all of OpenAI's GPU needs. But that exclusivity ended in 2024 when OpenAI signed another huge contract with Oracle to get more GPUs. But turns out even that was not enough, right? This year, they signed a partnership with Coreweave, and they're also in talks with Google to get TPUs for additional compute capacity. And you guys might know of this. Sam also put out like a tweet saying that, hey, whoever has GPUs, please call us. We need more of them, right? So clearly, having 4 clouds is not enough. This GPU shortage that we are going through is very, very real. And it's probably hitting you too, right? But the question is, what if you're not OpenAI? Say you are not operating at that scale, but you still need a lot of GPUs, right? Even then, getting GPUs today is really hard. If you're a team which just wants to, say, fine-tune some models, serve some models, maybe run some batch jobs, and you want to get GPUs somewhere, the cloud landscape out there is exploding, right? You have more than four actually hyperscalers. So you have AWS, GCP, Azure, Oracle Cloud, which are the classic cloud providers. But you have an emerging wave of neocloud giants, providers like Coreweave, Lambda, Crusoe, Nebius. They offer great GPUs at lower cost than the hyperscalers. And then you have a really long tail of other neoclouds, which are offering you GPUs, which can be up to 2 to 3 times cheaper, but maybe the performance is not that great, or they have like reliability or capacity issues. So this is like a really large search space to be picking your GPUs from, right? And even if you pick someone from here, you'll need to adapt your AI infra and AI work to work on different clouds as you move between them. So in essence, to take advantage of the capacity available across all clouds and save costs, your AI platform, first off, needs to be agnostic to any cluster, any cloud. It should be able to run on any infrastructure that you bring to it, right? And naturally, it needs to be multi-cluster because you're not going to get capacity in just one cluster. It'll likely be spread across different regions, even within the same cloud. And then finally, because you want to take advantage of pricing differences and capacity availability across different clouds, it needs to be multi-cloud aware, your AI platform. However, this word multi-cloud AI platforms is very loaded, right? It's very hard. There's lots of questions around like, hey, where do I find GPU capacity? What cluster manager should I be using? How do I manage, say, access control across different clouds? How do I run specific AI workloads? For example, distributed training needs gang scheduling. Do I make that work in this like multi-cloud scenario? So traditionally, it's been a very hard problem. But in this talk, what I want to convince you is multi-cloud AI platforms can be relatively easy. There's still a lot of work, but they can be easier than what they seem like. Right? And in this talk, I'll be walking you through the entire process, right? From getting GPUs to installing your cluster manager, and then finally managing these multiple clusters across clouds. So let's start simple, right? Let's look at what an AI platform is. In essence, you have an AI engineer who has some workload, PyTorch, Ray, or even their own Docker container. And you have some GPUs that you want to be able to run these workloads on. And the goal of your AI platform really is to act as this bridge between connecting AI engineers to the GPUs that they need to run their workloads, right? But this is an oversimplified view, right? Things are never this easy. Let's start at the right end, where I'm showing like one GPU. It's never going to be the case that you'll just use one GPU for your workloads, right? There's going to be many GPUs in your entire infra stack, and these GPUs will likely be spread across different clouds because of the same reasons of capacity and cost, right? So let's look at what's like the best way to get GPUs in 2025. So if I was giving this talk 5 years ago, I would say, yeah, just go to your favorite hyperscaler, ask them for GPUs, and they'll probably hand you like a bunch of V100s or P100s or K80s, whatever was hot that time, right? But things have changed. Everyone's now rushing towards the neoclouds to get GPU capacity. OpenAI, Microsoft, all the big names are going to neoclouds. But why is that the case? Why are people going to neoclouds, right? So AI workloads have three main needs. First, they need GPU capacity, of course, so that you can run your workloads. Second, they need high performance. Because now jobs are really big, they are really distributed, you need really good performance between nodes and on the interconnects that connects with all these different GPUs. And finally, you want the pricing to be reasonable. You don't want to be spending like an absurd amount of money just to get Llama 4 fine-tuned on your data. So let's go through each of these, right? On the hyperscalers, it's really hard today to get capacity. You have to go through multiple sales hoops. You have to sort of like convince them. You maybe even have to like sign long-term contracts just to get some capacity. Whereas on the neoclouds, you just go to their cloud portal, give them your credit card, and they'll like instantly hook you up with like H200s. Performance on the hyperscalers has also been slightly slower compared to neoclouds, though they're catching up now. This is about like a year dated now. But neoclouds offer you like 3.2 terabits per second InfiniBand right out of the box. Super easy to configure, just click a few buttons and it's like all set up for you. And finally, hyperscalers have traditionally been more expensive than the neoclouds, whereas neoclouds can be up to like 30 to 50% cheaper depending on how long of a contract you're signing. And this is just not me saying this. SemiAnalysis, a very well-trusted third party, put out this cluster max rating system where the neoclouds dominated that list. They were like the platinum and the gold tier, whereas the hyperscalers were more in like the gold, silver, and even the bronze tier. So to summarize, right, like if you're out there looking for GPUs, and I'm by the way, I don't work for any cloud provider, so you probably want to do multi-cloud. You want to go to different clouds, secure capacity, and one of the added benefits is you don't get logged in if you're like signing up with multiple clouds. You have very good negotiation leverage. Let's say 1 year from now, when you're renewing your contract, you can be like, hey, I have the ability to move between different clouds. Can you give me a better discount? Second, I would urge you to consider using neoclouds or even your own on-prem data center, right? It's going to be lower cost and possibly better performance. And one thing I would strongly recommend is benchmark your workloads on your clouds, on the clouds that you're choosing, right? So don't sign a contract right away. Do like a week-long POC with them. Run your own nickel bandwidth tests. Try to run your own workload to make sure like the end-to-end performance is really good. Cool, so let's go back to building our AI platform, right? Say you have secured the GPU capacity, but just having capacity is not enough. Now that you have these GPU capacity, you need to deploy a cluster manager, which can orchestrate and run workloads on the GPU capacity you just secured. So there's three big options here, right? Slurm, Kubernetes, or you could just use raw virtual machines. Let's walk through each of them, right? So Slurm, has been around for about 2 decades now. Really built for HPC workloads, and it's in operation at like some of the biggest supercomputers out there. And it offers like really advanced scheduling capabilities, like you can do like fair sharing between nodes, priorities, preemption, and so on. But the challenge here is like because it was built 2 decades ago and containers were not really a thing. You probably had C groups, but like nobody was really using them. It gets really hard to guarantee isolation between jobs. So if you operate a Slurm cluster, you know the pain of sort of like forcing everyone to use the same dependency set, and then people complain that, hey, I want a different CUDA version or a different PyTorch version, and so on. The other thing with Slurm is it's sort of built for fixed size clusters. So think like large supercomputers. But in today's world, you want to elastically scale up and down to sort of like control your costs. And then finally, Slurm wasn't really built for serving. It's really more for like long-running batch jobs. On the other hand, Kubernetes, came out a decade ago, super popular. Like, it's kind of like the de facto standard for building anything cloud native. And it's really elastic, has native auto-scaling support, works with most cloud providers seamlessly. And it provides like really good isolation, and that's important for like AI workloads and AI research workloads specifically, because people want to be experimenting with like different dependencies. They want to have their own environment that they can like play around in. However, I don't need to say this, but there's like enough memes out there about how Kubernetes is so hard to use for newcomers. It has a very steep learning curve, especially for people who are not into infra systems, right? And it doesn't offer interactive dev. Like you can do kubectl exec to get into a pod, but you can't really like SSH into a pod directly, and that makes it kind of clunky for AI researchers to use. And finally, there's no gang scheduling, right? For example, distributed training jobs need all or none scheduling semantics when they're launching a job. So if you end up requesting 16 nodes, Kubernetes might grant you like 8 pods running out of 16. And as a result, you may have other jobs which may end up in a deadlock trying to get the same resources. Of course, you have like plugins which can resolve this now, but I'm just talking about like vanilla Kubernetes. Finally, you have virtual machines, right? You can be like, okay, I'm not going to use any cluster manager. I'm just going to like, build my own stack on raw virtual machines. Very simple abstraction, very well understood by everyone. And it's highly elastic. Like literally, that's a unit of compute you get from different clouds. But it gets really hard to manage because you are now dealing with raw virtual machines. So there's like a bunch of SSH keys flying around. You have to like manage how you get access to them. And they require a lot manual orchestration. So you'll need to use something like Terraform to set up like scripts to instantiate these machines and scale them up and down. So it's a hard call picking between these. I'll just give out some general tips, and you guys should make the call for yourself. I would recommend using a mix of Kubernetes and Elastic VMs, simply because it's like a cloud-native stack and much easier to scale up than Slurm today. And try to use managed Kubernetes where possible, because you don't want to be in the business of like operating a Kubernetes cluster. You really want to be building like an AI platform that your engineers can easily use. And then finally, if you have some legacy workflows or there's some research code that really relies on Slurm, maybe that's one of the reasons why you'd want to like go for Slurm. Cool. So looks like at this point, we have GPUs, we have a cluster manager deployed. And at this point, most of us infra folk would say, OK, great, now you can like use kubectl or SBatch to sort of like submit jobs. It's ready to go, start using it, right? But your AI engineers would probably disagree, right? First, as much as we folk love Kubernetes and Slurm and all these like cluster managers, it's really hard for AI engineers to be using those systems, right? They just want to work on their model, their code. They want to get like a SSH box they can access, but they don't want to like learn kubectl. They don't want to learn like how Slurm works. Second, your infra is now scattered across different clouds, right? And this is the complexity of multi-cloud, because now how does the AI engineer know which cloud should they be going to talk to, or like which cluster should they be submitting their jobs to? And finally, there's a few key operational features that's still missing from this platform, right? You don't have any kind of like admin policy enforcement so that you can control who runs what. You don't have any kind of access control. There's no SSO here. How do you do logging of jobs? How do you run distributed jobs? Who does the queuing in this whole like entire stack? And this problem gets even worse in larger teams, right? Because now there's N engineers interacting with K different clusters, and then it becomes like a mess of like, hey, where do I launch my job? How do you coordinate between teams and jobs, or like who gets to run on which cluster and so on? But the good news is, like in most systems problems, good abstractions can really help you solve this problem. And this is kind of what an AI platform does for you, right? It provides a friendly interface for AI engineers to submit their jobs so that they have like one point of interface that they work with. And the AI platform sort of takes care of like running across different infrastructure, different clusters. And in addition, like this AI platform provides you like additional features and capabilities like scheduling, job execution, policy enforcement, and so on. So let's look at some popular AI platforms, right? So most of these AI platforms have been traditionally built in-house, right? Like Meta has something called Mast. They published a paper about it, and I believe OSTI or some conference. Shopify has Merlin. Uber has Michelangelo, which I believe they talked about yesterday. But the challenge here is these systems are not open source, right? Like if you don't work at these organizations, you and I, we can't use them. And they are incredibly expensive to build and maintain. They take like multiple man years to build these, and then you have like a constant maintenance overhead of making sure they're up and running. So this is where SkyPilot comes in, the open source project I work on. right? SkyPilot is an open source system to simplify and scale any infrastructure. And it really acts as like one control plane to use your AI infra anywhere. And it works pretty simply, right? Like the AI engineer sort of brings in their own workload. So, it can be a Ray program, it can be their own Docker container. If you are using RL, you can do rollouts with whirl and so on. You bring your AI code, and then you give it to SkyPilot saying that, hey, I need 8 H100 GPUs to run this. And then SkyPilot takes care of orchestrating it across all your infrastructure. Right? It'll take care of provisioning the instances. It'll take care of running the job and then cleaning up the job after it's done. And in doing so, it also provides team-based features around like people can see who's running what. You have like advanced admin policies you can enforce and so on. Just to provide some background, we started this project about 3 years ago when I was a PhD student at UC Berkeley's Sky Computing Lab. And we have come a long way since. We have Shopify, who's internally using SkyPilot to run most of their workloads. The CEO of Shopify tweeted this day. He really enjoys using SkyPilot. And it's not just big enterprises, but also AI natives like Hippocratic Abridge, like multi-billion-dollar AI startups using SkyPilot to run their workloads. So let's look at how SkyPilot works, right? Like how do you actually launch GPUs and projects through SkyPilot? What makes it really easy? So in SkyPilot, our goal was to make it super easy to quickly spin up any GPU anywhere, right? And it's a CLI tool, so all you need to do is you say sky launch. You give it an infra name, say Kubernetes, and then you request what GPUs you need. So in this case, for example, it will run on Kubernetes and get me 8 H200 GPUs. Now, if I want to switch to a different cloud, all I need to do is change this one flag. So from Kubernetes, I can go to like AWS, Azure, GCP, Nebius, any of the neoclouds or hyperscalers. Similarly, if I need to change the accelerator from like H200 to something else, I just change this one flag and boom, everything just works. And one of the biggest benefits here is like it really makes it easy to get a dev box to sort of like get your workloads up and running. So for example, I can give we create what we call like SkyPilot clusters. Think of it as like a virtual cluster abstraction that you can launch on top of your existing clusters. And then you just do sky launch, give it a name, dev. And then once this is done, you can very simply just like SSH dev. SkyPilot takes care of all the key management. It takes care of like setting up your SSH config, doing all the tunneling and so on. And the cool bit is because you have like native SSH access instead of like kubectl exec, you can connect third-party tools like VS Code or Cursor directly to get like an interactive development environment on your remote machine. And now say if you don't want to deal with different clouds, you just remove the infra flag. Oops, there's a typo there. That should be GPUs. You just say, hey, I need 8 H200 GPUs, and then SkyPilot looks across all your infrastructure and will provision this dev box for you. More concretely, once you're done like developing or having like an interactive session, you can create what we call AI project, right? So a typical AI project has some working directory, which has some code. You have some dependencies that you install with pip, conda, uv, whatever you want to use. And then you have some program that you actually want to run, like some training script. SkyPilot translates these very nicely into simple portable YAML. So the idea is, you specify a local working directory, some setup that you want to run, and a run section. In addition, you state what resources you need. So you say something like, I need 8 H100s. And optionally, you can also mount cloud buckets. Like you can bring your own S3 buckets if you want to attach them. And once you have this YAML, all you need to do is do sky launch project.yaml, and then SkyPilot will take care of like shipping your code over there, provisioning an instance. It can be a VM or Kubernetes, up to you. And then it'll ship all the code and data, run the setup, run the job, get you the logs, and then clean up the job once it completes. And this makes it super easy to scale distributed training when you need to, right? So here's a very simplified example of how do you do full fine-tuning of, say, GPT-OSS, OpenAI's recent open source model. You state your resources, but in addition, you state this flag called num nodes. So you say, I want to run this workload on 4 nodes, right? And if you need to scale up to, say, 128 nodes, all you need to do is change this one flag, and you can instantly scale up. And the cool bit here is like we provide Slurm-like convenience. So Slurm has a lot of useful environment variables that you can set, that are automatically set by the Slurm runtime. For example, how many nodes exist in the cluster, what's like the rank of the worker that's running this code, and so on. We provide very similar variables, so it makes it very easy to run your workloads. And on the infra side of things, it simplifies the stack, not just for AI engineers, but for the infra people too. Because say if you do Sky Launch, right, and you specified some GPUs, SkyPilot has an intelligent failover logic, right? So if your cluster is full, the first cluster it tries, it'll automatically try the next cluster that's configured in your setup. And if that's also full, it can automatically burst to the cloud and get VMs and then scale them down once it's done running the workload. So think of it as like one control plane that automatically cycles through all your infra to find capacity wherever there's available. So let me do like a quick demo so that it's easier to visualize what's going on. So here's my terminal, right? I can show you I don't have any kubeconfig configured right now, but I do have a working kubeconfig, right? So all I need to do is I copy my kubeconfig to like the regular kubeconfig directory. Now I do have access to it, as you can see probably here. Great, so I have access to my cluster. Now to set up my Kubernetes cluster with SkyPilot, all I need to do is run skycheck, right? What this will do is SkyPilot will check what credentials are configured on my machine or on a remote API server if this is deployed as a remote API server. And now it's showing that, okay, I found AWS credentials, GCP credentials, I found 2 Kubernetes contexts that I can use, and I also have access to Nebius VMs. Great, so now that I have this, I can very simply run Sky Launch, the same thing I just showed you, say dev, with 8 H200 GPUs, and I'm asking it to copy the current working directory. So let me actually show you my current directory. My current directory has just like some code I wrote locally on my machine, right? So I'm just going to go ahead, Sky Launch this. And now SkyPilot will run its optimizer, which will look at all the available infra options, what GPUs they're offering, and then it'll show me a list of where all it can run the workloads, right? So it's showing, hey, I have 2 Kubernetes clusters, one on Nebius, one on Coreweave, that I can try. It's going to try the Nebius cluster first. But if those clusters are not available, it'll automatically burst to the cloud running on Nebius. That's going to cost me $28 an hour. If that's not available, it'll go to like GCP and AWS. So I'm going to say, yes, go ahead. SkyPilot will now take care of the actual orchestration. It'll spin up the pods, get the copy my current work directory there, get everything up and running. So at this instance, SkyPilot is basically provisioning the pod, installing all the runtime dependencies, and then it'll just take a minute to sort of like get it up and running. So now it's saying it's initializing. Let's just give it a minute. And with this, let's just give it a quick minute. Wi-Fi should be connected. Okay, while this runs, let me show you the SkyPilot dashboard, which provides you like a single pane of glass to sort of see what's up and running. So you can see I just created this cluster called dev, which is being launched on a Kubernetes cluster. But at the same time, I have a bunch of other jobs that I was running. I had Alice from my team who was running, say, a batch inference job. Bob was running some pre-processing job. So I can click into these and very easily see what job they were running. So I can see, hey, there was, Bob launched a job, setting some environment variables and so on. I can click into his job and sort of see the logs of like how his training run went and so on. And this provides me like a single pane of glass to sort of see everything that's going on. Let's go back to the talk since we are running out of time. Cool. So that was a quick demo of how SkyPilot works. But to summarize, right, if you want to build an AI platform, the best way to do it is to first get capacity, GPU capacity from neoclouds, or bring in your own hyperscaler or on-prem resources. The next thing you need to do is set up Kubernetes or some kind of cluster manager, or you can just even directly use VMs if you're using an AI platform that can work with VMs. And then finally, deploy a layer like SkyPilot, which simplifies AI infrastructure for your AI teams. At the same time, it allows you to scale your infrastructure on the back end across different clouds, different clusters. And that's it. With that, I hope you get like a simple and scalable multi-cloud AI platform, which provides a unified interface for your AI teams, but also is able to run on any infrastructure that you bring to it. Cool. With that, I'll open up the stage to any questions.